Yeah. All right. So the first thing, number one thing to remember is there's a quiz on Thursday. Oh, hold on. Come on, OneNote. That's a new one. Okay, so quiz 2 is Thursday. So remember to look back over your notes and identify things that I seem to be trying to emphasize. Definitions, lists of things that say notice or remember, stuff like that. That's what I try to focus on these quizzes.
Is it obtrusive, like circular?
Oh, yeah, is there a cutoff? That's a good question. Let's just go all the way up till, okay, why not?
Why not?
It's only like 2 more pages, you know. Okay, so, and now let's go through the exam. I'll just go through it problem by problem. Overall, people did well. I mean, I was happy with the scores overall. If you think that maybe I misgraded something, which certainly happens, or if you just have questions about something, feel free to come talk to me about it. Okay, so number 1 in exam 2, a ball is launched from 2 meters off the ground at a speed of 15 meters per second and an angle of 30 degrees above the horizontal. So this is 2 meters. It's launched. Okay, hold on a sec. I know I just saw yours, Anwar. Okay, so this angle is 30 degrees. And this object is going to start out at that angle. And all we're trying to calculate is how high the object is at its highest point. Okay, one more. Regine. And I'm going to put the coordinate system the same way I always do on the ground underneath where it is when it's launched. Time equals 0 is going to be the launch. Time final is when it reaches the highest point. We're going to list out what we know and what we want. We don't know how long it takes to get to the highest point. We know the acceleration is 0, negative 9.81. We know that the position at time equals 0 is 0, 2. We're trying to find the y component of the final position. The initial velocity is the speed, 15, times cosine and sine of 30 degrees. So that comes out to be 12.99, 7.5. And then if you're looking for the highest point, then as soon as you see something about the highest point, you're waiting to write this down, just itching to write this down. And finally, it's time. Finally. VFY is equal to 0. And you can find PFY using this equation, 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So we have negative 19.62 times the quantity PFY minus 2 is equal to 0 squared minus 7.5 squared. Divide both sides by 19.62, add 2 to both sides, and you get PFY is equal to 4.87 about meters. By far the most common mistake people made was just from the start not treating this as a two-dimensional problem, treating it as a one-dimensional problem. And then, so that has the basic effect of treating the y component of your initial velocity as 15, which, you know, just sort of throws you off from the start. Anybody have any questions about that one? Then the second one is the friction problem. You have an angle of 25 degrees between the horizontal and this incline. And you have a 10 kilogram block sliding on the incline, and we know that it's sliding up the ramp. And we want to calculate the acceleration vector and then figure out if it's speeding up or slowing down. We're going to use a rotated coordinate system. And so that means that we're going to have sort of a funky expression for the weight force. So let's figure out what that's going to be first of all. So the weight is straight down. If this is the 270 degree line, you can see that this weight force is 25 degrees from the 270 line, like that. So if you're going counterclockwise from the x-axis, you go 90, 180, 270, and then another 25. So our weight force is going to be 98.1 times the cosine of, that's 295, and 98.1 times the sine of 295. And that comes out to be 41.46 for the x component, negative 88.91 for the y component. Okay, so now we can go to Newton's second law. The components for everything else are simple. So we have the weight force, 41.46, negative 88.91, plus 0n, plus, I didn't write this down, but the coefficient of friction is 0.3, and then you multiply that by the normal force, and then 0 for y. That's in the positive x direction because it has to be, oh my gosh, I didn't even draw a free body diagram. So stupid. I think that's the first time I've ever, I just got too excited, but I think that's the first time I've ever made that mistake because I love drawing free body diagrams.
Very.
Yeah, I know. It's fun. It's just plain fun. You got the weight force, the normal force, and since the velocity is up and to the left, the friction force has to be down and to the right, and that's 0.3 times n. So the way you always do this now is solve for n using the y equation. N is equal to 88.91. Then plug that into the x equation. 41.46 plus 0.3 times what we just figured out for n. Is equal to 10a. So a is equal to positive 6.81 meters per second squared. That's the value of a. This is the acceleration. We just have to plug a in. And so we get an acceleration vector that is 6.81 for x, 0 for y. Or in other words, you know, it's in the positive x direction with a magnitude of 6.81 meters per second squared. And then speeding up or slowing down, well, the acceleration is in the positive x. The velocity is in the negative x, so it's slowing down. Anybody have any questions about that one?
So, question. We don't use the magnitude for the acceleration at the first.
Yeah, when you calculate that variable a, you're calculating, well, you're really calculating not just the magnitude because it also can come out to be negative, but you're calculating the a value that when you plug it into this vector, it gives you the acceleration vector. And you can always represent a vector in either of those two forms. You don't have to do both of them, you know. You can give the components like this, or you can draw the direction and give the magnitude. Okay. And then the third one is two carts in contact with each other on a horizontal surface. This one has a mass of 2 kilograms. This one's 5 kilograms. We have a 30 Newton force here. A couple of people treated this like it was 30 times the normal force, the way it is in a friction problem. In problems like this, I'm never multiplying by the normal force, but I think I might have taken off a point for that. And then thinking about it later, I'm like, oh, you know, that's just sort of a misunderstanding. So if you treated this as 30 times the normal force and I took a point off, come talk to me and I'll give you that point back. But for future reference, unless it's a friction problem, you're never going to be multiplying something times the normal force. Okay. And we wanted to calculate the acceleration vector and then the force vector applied to the 5 by the 2. To get the acceleration vector, we'll isolate the whole system as a single thing. We have a weight force down of 7 times 9.81, so that's 68.67. We have a pushing force up that I'll call N total. And then we have a 30 Newton force here. So Newton's second law says 0, negative 68.67 plus 0n plus negative 30, 0 is equal to the mass times the acceleration. And the acceleration is a0 because it's moving along the x-axis, not along the y-axis. To find the acceleration vector, we're just figuring out, this is the acceleration vector. And so you can see that all we need to calculate is that variable a. So we're going to use the x equation. So negative 30 is equal to 7a. Divide both sides by 7, and you get a is equal to negative 4.29 meters per second squared. And so the acceleration vector is negative 4.29 for x, 0 for y. Or in other words, it's in the negative x direction with a magnitude of 4.29. And now we want the force applied to the 5 by the 2. You could get this by isolating either one of these if you keep Newton's third law in mind, but it's maybe a little more straightforward to just isolate the 5 kilogram in this case, so that's what I'm going to do. So we have a weight force of 49.05, a pushing force from the ground that's not the same as the total pushing force on both of them, so I'm going to call this N5. We have the 30 Newton force here, and then we have a pushing force from the 2 over here that I'll call R, and that's what we're trying to find. So Newton's second law says R0 plus negative 30, 0 plus 0, negative 49.05 plus 0 N5 is equal to the mass, 5, times the acceleration vector we just figured out, negative 4.290. This is the force vector we want, so all we need to figure out is R to plug it in there. So we have R minus 30 is equal to 5 times negative 4.29, and you get that R is equal to 8.55 newtons. So the force on the 5 by the 2 is 8.550. Or in other words, it's in the positive x direction with a magnitude of 8.55 newtons. While we're here, let me just show how you would figure this out if you isolated the 2 instead, a free body diagram of the 2 kilogram cart. You have a weight force down of 19.62. You have a pushing force up that I'll call N2. And then the 30 Newton force isn't applied to the 2. It's applied to the 5, so it doesn't show up. But the 5 kilogram does push on it. So we have this force here. Newton's second law says negative R0 plus 0, negative 19.62 plus 0 N2 is equal to the mass, 2, times negative 4.290. And you get R is equal to, well, there's some round off error there. I've rounded off a bunch of stuff, but let's pretend that it gives us 8.55. The way I have it written, it really gives 8.58. Then you plug it back into this to find the force on the 2 by the 5. So we got negative 8.550, or in other words, it's in the negative x direction with a magnitude of 8.55. And Newton's third law then says, if you have the force on 2 by 5, then the force on the 5 by the 2 is just the opposite of this, so positive 8.550, or in other words, it's in the positive x direction at 8.55. So even though the free body diagrams look different and whatever, you can calculate it either of those ways and it'll come out the same. Anybody have any questions about that one? I can't remember there being any common problems that I saw a lot on that one. And then the fourth one, the last one, is the one with the ledge and the pulley. And you have a rolling cart with a mass of 1.5 kilograms. And then a hanging mass of 1 kilogram. And we wanted to figure out the acceleration of the 1.5. So pick one of these as a first body. It doesn't matter which one. There's a weight force of 14.715. A pushing force from the ground, N, and then a pulling force from the cable, P. Newton's second law says P0 plus 0, negative 14.715 plus 0N is equal to 1.5 times, this is the first body, so all we have to do is figure out, is this moving along X or Y? And we're just going to call A positive in whatever along whatever axis it's moving along. This is moving along x, so we'll just call this a0. And we only care about acceleration, so I'm only going to keep the equation that says t is equal to 1.5a. And I'll set that aside. We can't solve that because it's two variables. So now we have to go to the next body. The weight force is 1 times 9.81. The cable is pulling, and the magnitude of that force, since it's the same cable, is the same as on the other body. And so Newton's second law says 0 positive t plus 0 negative 9.81 is equal to 1 times the acceleration. And this is the part that's easiest to make mistakes on. But now what you have to think is, okay, our first body, if that moves in its positive direction, so that would be in the positive x direction, where does the hanging mass go?
Negative.
Yeah, negative y. So I'm going to write this as 0, negative a. Okay. And so then the useful equation here says t minus 9.81 is equal to negative a. Now I'll solve this box system of equations by replacing the t in the second equation with 1.5a from the first equation. So 1.5a minus 9.81 is equal to negative a. Add a to both sides, you get 2.5a. Subtract 9.81 from both sides. And you get that a is equal to 3.92 meters per second squared. We want the acceleration of the rolling one, so plug that a value in here. And you get that the acceleration vector is 3.920. Or the positive x direction with a magnitude of 3.92. Any questions about that one? Okay, I have a question, an interpretation question. How did I know that this system was going to be accelerating to the right and down when I chose this acceleration for the first body? You know what I mean? Yeah, I mean, that's how I chose. I mean, I guess the answer I'm looking for is I didn't know which way. I don't have to know which way it's going to accelerate. I just chose, as a totally arbitrary thing, I just chose a positive direction to put that A in for the first body. And then I figured out the relationship between if it accelerates in the positive direction, the 1 kilogram accelerates in the negative direction. So what if I did this and then it turned out that the whole system was accelerating the other way? It would still work because we'd get a negative value for A, which would say that the rolling thing was accelerating to the left. We'd get a double negative for the acceleration component of the hanging thing, which means, so now we'd have the acceleration of the 1.5 moving to the left and the 1 moving up, accelerating up. So the answer is, I didn't have to know anything about the direction of the accelerations. All I'm figuring out with those signs is the relative. If one's going positive, the other one's going negative. If this one's going positive, this one's going negative. That's what you're doing when you find the direction of that second body's acceleration. Okay. Any questions about the test overall? Well, now we're going back to conservation of mechanical energy. I'm going to do another example problem where the potential energy we're going to use is gravitational. Then I'll do an example problem, the first one you've seen where it's a spring. And then if I still have time, I'll do sort of a more complicated thing where mechanical energy gets mixed in with some other stuff that we know how to do. Okay, so let's say that there's a skier moving along the flat, and the skier is going to get to the top of this 1.5 meter hill. Okay, so at the bottom of the hill, the skier's going this way. If the skier wants to have a speed of 5 meters per second at the top of the hill, what needs to be the speed at the bottom of the hill? Okay, well, it's always a good idea, first of all, to think, does conservation of mechanical energy apply to this problem? So you can think about it a couple ways. One way you can think about it is, are there any forces on the skier during this process, during this motion, besides gravity, a normal force from the ground, a centripetal force in a circular motion, or a spring force? Those are the only 4 forces that we can deal with in conservation of mechanical energy. So let's think about a free body diagram for a second. There's a weight force, and there's a pushing force. This weight force is conservative. We have a potential energy function for that, so that's fine. This normal force is non-conservative, but it does no work. So we can use conservation of mechanical energy for this. So now I'm going to set up a table with an instant 1 that's going to be at the bottom of the hill, and an instant 2 that's at the top of the hill. To represent the potential energy due to gravity, remember that we need to choose something to be our zero height, okay? And it doesn't matter what you choose. I always choose the lowest point in the motion. So I'm going to call this h equals 0. But it's good to remember that no matter what you choose as your h equals 0, you're going to get the same final answers. Okay, so at the bottom of the hill, let's calculate the gravitational potential energy. That's equal to the mass times 9.81 times, what's the height at the bottom of the hill?
0.
Yep, 0. So there's 0 potential energy at the bottom of the hill. And now we'll calculate the kinetic energy. That's 1/2 times the mass of the skier, and we don't know what that is. But what we're going to see is that it cancels out. And so if the m cancels out of the equations, it tells us that the answer would be the same no matter what the mass of the person is. And then we don't know what the speed is. We're trying to calculate that, so I'll leave that as capital V. Then at the top of the hill, the gravitational potential energy is the mass of the skier times 9.81 meters per second squared times the height at the top of the hill, which is 1.5 meters. So this comes out to be 14.715 times the mass of the skier. The kinetic energy at the top of the hill is 1/2 times the mass of the skier times the skier's speed squared at the top. What do we want for the speed at the top?
5.
Yep. So this is going to be 5 squared. And so we get 1/2 times 25 times m. So that's 12.5 times the mass of the skier. And now we can add up all the stuff on the left and set it equal to the sum of all the stuff on the right. So we have 0 plus 1/2 mv squared is equal to 14.715. That's a terrible 5. 14.715 m plus 12.5 m. Since everything is multiplied by m, you can divide both sides by m and those go away. And that's where you see, okay, the skier could be 200 kilograms or 20 kilograms, and the answers will all be the same. So we get 1/2 times v squared is equal to 27.215. Multiply both sides by 2, and you get v squared is equal to 54.43. Take the square root of both sides, and you get that v is equal to plus or minus 7.38 meters per second. And this is a speed, so we just want the positive one. We assumed that there was no friction or air resistance or anything, but with those assumptions, in order for this skier to be at 5 meters per second at the top of the hill, he has to be at 7.38 meters per second along the flat. Any questions about that? Okay. It's hot in here, actually, isn't it? All right.
Sure.
So let's do one with a spring. So let's say that we have a rolling cart with a mass of 0.2 kilograms. And it's attached to the wall by a spring that has a spring constant of, let's say, 400. And the units of that spring stiffness constant are newtons per meter. And by the way, here is how you would get that spring stiffness. If you take a spring and attach it to some mass, okay, the effect is going to be that the spring stretches. And so let's say that we're going to call this amount of stretch X, okay? Well, the spring stiffness is just equal to the weight of that mass divided by how much the spring stretches, okay? So if the spring is really stiff, then that X for any given mass that you hang from it is going to be relatively small, you know? And so if you're dividing by a small thing, you get a big spring constant. On the other hand, if the spring is really flexible, you're going to get a big value of X. And so a big value of X would give you a small k. So that's what that k means. Okay. A big value means the spring is hard to stretch. It's really stiff. A small value of k means it's easy to stretch, flexible. And let's say that with this system over here, we pull the cart 0.01 meters to the left and release it from rest. How fast is this, I guess, the cart? How fast is the cart moving at its fastest? Okay. Well, what's going to happen? Can you sort of visualize? We're ignoring any friction, things that are going to take energy out of this system. So if you pull this thing and let go of it, it's just going to oscillate back and forth. And somewhere in the middle of that oscillation, it's going to be going its fastest. Then it'll slow down, turn around, and just keep doing that forever because we're not losing any energy during an oscillation. You know, in real life, you'd lose a little energy each oscillation, and eventually it would stop. But to us, that doesn't happen. Okay, so the first thing we have to think about is, can we use conservation of mechanical energy for this? And so again, let's start with the free body diagram and think about the forces acting on it. There's gravity, a normal force from the ground, and then there's a spring constant that's sometimes going that way, sometimes going the other way, but spring constant. And now let's think about whether these are allowable in conservation of mechanical energy. mg, the weight, that's a conservative force that we have a potential energy function for, so that's good. The normal force, that's non-conservative, but the work is equal to 0, so that's okay. This spring constant is conservative, so we have a potential energy for that, and so we're good. Okay, this should work. One thing we always have to do if gravity is part of these problems is choose a height equals 0. Well, let's just choose our height equals 0 to be the height of this thing. I mean, notice that the height never changes. So I'm going to call this h equals 0. And what we're going to see is that the gravitational potential energy doesn't even come into this. Okay? But, you know, you might not see that right away. So let's just put it in and see what happens. And then we'll think about our two instants. Instant 1 is when it's pulled to the left. Instant 2, the way I'm going to do this is I'm going to just choose some arbitrary instant in the motion. So I'm going to just leave x as a variable and leave v as a variable. And then we're just going to figure out when that v is going to be the biggest. Okay, so this instant is arbitrary. Okay, when it's pulled back, the gravitational potential energy is mg. It's at 0 height, so times 0. So there's 0 gravitational potential energy. Then the potential energy due to the spring, that's 1/2 times the stiffness, 400, times x squared. Now remember, x is how far the spring is from its resting length. So we stretched it out 1 centimeter, so that's x. Okay, so I'm going to write this as 0.01 squared. And that gives us a potential energy of 0.02. And anyone remember what the SI units for energy are?
Joules?
Joules, right. And then the last thing is the kinetic energy. That's 1/2 times the mass. We know the mass in this case. What was it, 0.2? What's the speed at the instant it's released? Released from rest. So 0. So the kinetic energy when it's released is 0. And now we'll go to this arbitrary second instant. The gravitational potential energy, it's still at the same height, so that's still equal to 0. The spring potential energy, we don't know how far the spring is from its resting length at this arbitrary instant, so I'm just going to leave that deformation as x. Okay, and we'll see how it works when we get through it. But so we have 1/2 times 400 times x squared, or in other words, 200x squared. And then last is the kinetic energy. That's 1/2 times the mass times the speed squared. That's what we're trying to find. So I'll just leave that as V. And now we can plug this all into conservation of mechanical energy. So we have 0 plus 0.02 plus 0 is equal to 0 plus 200 x squared plus 0.1 v squared if you multiply the half and the 0.2. Okay, I'm going to multiply everything by 10 first of all. And so I get 0.2 is equal to 2,000 x squared plus v squared. And then I'm going to subtract the 2,000 x squared from both sides. And then I'm going to take the square root of both sides, and we get that the speed is equal to plus or minus square root of 0.2 minus 2,000 x squared. And this is a speed, so we can forget about the -1. Okay, so this tells us at whatever distance the spring is from its resting length, what's the corresponding speed. That x is always positive and we're squaring it anyways. So any x value is just going to subtract from this 0.2. Okay, so when do we get the biggest speed? We get the biggest speed when x is equal to 0. So the maximum speed is when x equals 0. Does anyone have any questions about that? Do you follow the thinking there?
Yeah, one more time.
Yeah. Well, we have this relationship between speed and deformation of the spring. And since this expression for the this square root expression gets smaller for any x value, you know, the biggest this can be is when x is equal to 0. Okay, and so since we're looking for, you know, how fast is it moving at its fastest, we can see now that its fastest is going to be when x is equal to 0. Okay, and so the answer is the fastest it's going to move is the square root of 0.2. Can someone tell me what the square root of 0.2 is? Do I know that? No. 0.44 or something?
447.
Okay. I'll just call it 0.45 meters per second. So with this specific spring, you pull it back a centimeter, the fastest it'll ever be moving as it's oscillating is 0.45 meters per second. Yeah.
So with my thing is that there's still a square with the 2,000 x squared. Like, wouldn't that cancel out the square root? Or
It doesn't work like that, actually.
cancel it out?
The way it works, if you remember this, yeah, it doesn't cancel that out. Think of it like, in order for this to give a real, how many people here have talked about imaginary numbers in math classes? Most people. Well, any imaginary answer to this is meaningless to us, you know. So this only makes sense for answers that are real. And it is going to be real as long as that x is between 0 and 0.01. Okay.
So like if you tried to, it'd just give you an imaginary number.
Yeah, that's right. If you used a bigger x value than 0.01, it would give you an imaginary answer. And what that really means is just, well, if you pull it back a centimeter and let it go, it's never going to be more than a centimeter from its resting length. It's not like you'll let it go and then it'll get bigger and bigger oscillations, you know? Yeah. I glossed over a little bit of that, but any other questions about this? Okay, I want to do one now that combines a few different things. So you can see how conservation of mechanical energy can fit into bigger problems where you're using other techniques and stuff too. So let's say that we have this mass on a string and a person is swinging this around in a circle. Okay, so this is going around in a circular path. And let's say that the length of the string is 0.2 meters, 20 centimeters. And let's say that the mass of the ball is 0.4 kilograms. And I'm imagining this in a circle this way, so gravity is going to come into this problem. This is down. And we want to calculate the following stuff. So first, we want to calculate what's the slowest the ball can be moving at the top of the circle to maintain circular motion. We did an example like this once a couple weeks ago. We're gonna just do it again. But basically, like if it's going too slow at the top, it'll fall out of its circular path. It won't continue a circular path. And the slowest it can be going is when it's still in circular motion, but the tension in the cable is 0. Okay? If it's going any slower than that, the cable would have to push on it to maintain circular motion, and we know cables can't do that. Okay? After that, we want to calculate the speed, the corresponding speed at the bottom of the circle. So if that ball is at its minimum speed at the top of the circle, what's its speed going to be at the bottom of the circle? Gravity is going to make it speed up as it goes down. And then last, we want to figure out what's the force, what's the cable tension at the bottom. So you probably have intuition that if this string is going to break, it's always going to break at the bottom of the circular path. That's when the string is under the most tension. If you ever watch like men's gymnastics in the Olympics or whatever, every time there's a spectacular, they'll do their flips over the bar and recatch the bar. And if they don't catch it tight enough, they'll always fly off at the bottom. That's because the bottom of this circular path is where the most stress is applied to whatever's holding you to the bar, or in this case, to the hand. Okay, does everyone understand what we're doing? So basically, we're figuring out if you go as slowly as possible with this circle to still maintain circular motion, what's the maximum stress that string is under? That's what we're going to calculate. Basically, we're going to calculate how strong a string you need in order to have this mass swing through a circle. Okay, so for the first one, this is a circular motion problem. At first, we're talking about the top. At the top, the centripetal acceleration is this direction. The magnitude of the centripetal acceleration is v squared over r. Do we know what the radius of that circle is? 0.2, yep. So v squared over 0.2. And that's in the negative y direction, so the centripetal acceleration vector is 0, negative v squared over 0.2. Is there any tangential acceleration at the top of the circle? There's not. We've seen that in lab or talked about it in lab. This will be speeding up whenever it's on the way down and slowing down whenever it's on the way up. But at the top and the bottom, it's not speeding up or slowing down. So at this point, there's no tangential acceleration. Okay, so now a free body diagram. We have a weight force down of 3.924. And we have a cable force T. And in order to find the slowest that this can be going to maintain its circular path, we're going to set this T equal to 0. So Newton's second law says 0, negative 3.924 is equal to the mass times the acceleration, which is 0, negative v squared over 0.2. The y equation says negative 3.924 is equal to negative 2v squared when I divide 0.4 by 0.2. And so we get v squared is equal to 1.962. And so take the square root of both sides and you get v is about 1.4-ish kind of thing. Okay, so that's the slowest this can be moving at the top of the circle to maintain its circular path. Okay? If it goes any slower, it's going to fall out of the circular path. We didn't use any mechanical energy on that first part. But now we're to the second part, and we're going to use mechanical energy to figure out if it's going this fast at the top, how fast is it going at the bottom of the circle, okay? Okay, so what forces are acting on this as it goes through this path? There's a weight force. There's a cable force toward the center of the circle. This weight force is conservative. So that's good. We have a potential energy function for that. This cable force is non-conservative, but that's a centripetal force during a circular motion. So we know that the work is equal to 0 for that force. Okay, so we can use conservation of mechanical energy. So let's say instant 1 is going to be at the top of the circular path. Instant 2 is going to be at the bottom of the circular path. I'm going to call the bottom of the circular motion my h equals 0. Okay, so at the top, the gravitational potential energy is the mass, 0.4, times 9.81, times, what's the height at the top of the circle? 0.4, it's 2 times the radius, right? Can someone multiply that for me?
$1.569.
1.569. And that's in joules. And now at the top of the circular path, the kinetic energy is 1/2 times the mass of 0.4 times the speed of 1.4 squared. And so that is 0.2 times 1.962, so I think that is 0.3924. And that's joules. And then at the bottom of the circle, the gravitational potential energy. Well, what is the gravitational potential energy at the bottom of the circle? Since the height is equal to 0, this is going to come out to be 0. And we're trying to figure out the speed. So this is 1/2 times 0.4 times the speed we don't know squared. Add these all up and put them in conservation of mechanical energy. You get 1.569 plus 0.3924 is equal to 0 plus 0.2 v squared. And so we get v squared is equal to, this comes out to be 9.81. Take the square root of both sides, and v is equal to plus or minus 3.13 meters per second. So the slowest this ball can be going at the bottom of its path to maintain circular motion all the way through is 3.13 meters per second, like 7 miles an hour. Okay, that would vary depending on the length of the string you were using. And then the last step is we're trying to figure out the force in that string at the bottom. So again, we're going back to a circular motion problem. Now we're looking at this point. The centripetal acceleration is up. Its magnitude is v squared over r. 3.13 squared is 9.81. The radius of the circle is 0.2. And so that's an acceleration of 49.05 meters per second squared. As a vector, that's in the positive y direction. So the centripetal acceleration vector is 0, positive 49.05. Again, at the top and bottom, there's no tangential acceleration because it's not changing speeds. So this is the total acceleration. And now we'll go to a free body diagram. We have the weight force of 3.924 newtons down. We have the cable force, T. Newton's second law says 0 T plus 0 negative 3.924 is equal to the mass times the acceleration. And the y equation says T is equal to 3.924 plus 0.4 times 49.05. So T is equal to 23.54 newtons. And so if you have a cable that can't support this much force, it'll break at the bottom of the circle. Any questions about that? I mean, that's a super involved problem. I mean, compared to most of the problems we do, but you know how to do each one of those steps. And you can see that we couldn't do this problem before we started talking about mechanical energy. Okay, that's all.